Hi guys, welcome back to the KZN 2022 Paper 1 trial, and we are on question 4. So this question starts off with the proof of the geometric series. So I went ahead and worked through that already because it takes a little while to set it out. What we've got here is basically just proof that we need to learn, but there are some things that you can use as checkpoints to help you remember this, especially if your algebra is really good. So the first one here, the first equation says that the sum of this series is just the sum of all the terms in terms of a and r. So starting from the first term a, the second term is a times the ratio, and then we multiply by the ratio again and again and again. And the last term is going to be r to the power of n minus 1. So a times r to the power of n minus 1. And the reason for that, the reason why it's n minus 1 is, let's say we were going up to 10 terms, right? Then we would have the first term, we would multiply by the ratio 9 times, right? So we would have a times r to the power of 9 there. So 9 is 1 less than the maximum n, so it's n minus 1. And then the term before that is n minus 2, so that would be 8, and then 7, 6, all the way down to 1. Right? We don't know how many terms there are, so we have this gap in the middle with the 3 dots. The next step is to take that same sum and multiply it by r. So what we're doing here is actually an algebra trick. We are multiplying by r, and what that's going to give us is a bunch of terms that can cancel out with the terms in the first equation. So in the second equation, we've multiplied by r, the a has become ar became ar squared, so on and so forth. The ar to the n minus 2 would have become ar to the n minus 1. This ar to the n minus 2 would have actually come from ar to the n minus 3, which is not shown. Okay, so if you're wondering where that comes from, that's where that comes from. And then ar to the power of n, that is ar to the n minus 1 times r. Okay. So now the next thing to do is to actually subtract them, and for this configuration where it's r minus 1 and r to the n minus 1, you want to take the first equation and subtract the second equation from it. And what you get then is we take the left hand sides of both of the equations, r times Sn minus Sn, and then what happens here is a bunch of terms cancel out. So when we subtract the two equations, right, we get this. The AR cancels with the AR squared cancels with the AR squared, AR to the n minus 2 cancels with AR to the n minus 2, and the AR to the n minus 1 also cancels out. Okay. And then you can see what that leaves you with is in the second equation we've got ar to the power of n, and in the first equation we've just got a. So 2 minus 1, this is what we are left with over here. Then from here we are going to factorize out this symbol Sn, the sum, and when we factorize it out, it's going to cancel there, it's going to cancel there. We're left with r minus 1. Remember, when we factorize, that Sn is going to leave a 1 behind. Okay. And on the right hand side here we factorized out a, so we have a into 1 minus r to the power of n. The last thing to do then is just to divide out that r minus 1, so we get that fraction, and then it is proven. Okay, so the reason why they have that r is not equal to 1 there is because if r was equal to 1, it would break this expression. It would make the denominator equal to 0, and we know we're not allowed to divide by 0. Cool. Let's move on to 4.2. This one was also a bit of a tricky one. A lot of my guys battled with this one. The first two terms of a geometric sequence with a constant ratio r and an arithmetic sequence with a constant first difference d is the same. Okay, so there's a lot to unpack there. The first two terms of two sequences, one's geometric and one's arithmetic, are the same, and the first term is 12. So if we look at the arithmetic sequence, right, and the geometric sequence side by side, this is what we're going to see. The arithmetic sequence has a first term of 12, and so does the geometric sequence. Okay, then there's some unknown difference, but we do know that with an arithmetic sequence, we're going to be adding the difference, some unknown difference. That's going to be our second term. For the geometric sequence, we multiply by some unknown ratio. So this is going to be 12 times r. Okay, and that's what we know so far. So first term is 12. The second term for the arithmetic sequence will be 12 plus d, and the second term for the geometric sequence will be 12 times r. Okay, and that's it. They say write down the second and the third terms of each sequence in terms of d and r. So we actually don't want to put this first term in there because they didn't ask us for it. We might get marked down for that. We do want to put in the second term, which is 12 plus d, and then the third term is going to be 12 plus 2d, because there's two differences in the third term. So we add d again, basically. So this is term 1, and then term 2 is going to be 12 plus 2d. So this was only 2 marks, and I'm guessing that I'm guessing you get 1 mark for each of these, 1 mark for both of the terms in the arithmetic series, and 1 mark for both of the terms in the geometric series. But you can check the memo if you want to know that. So yeah, this is your arithmetic sequence over here, this is your geometric sequence. And then they say, if it is further given that the sum of the first 3 terms of the geometric sequence is 3 more than the sum of the first 3 terms of the arithmetic sequence, determine the 2 possible values of the common ratio r of the geometric sequence. So again, a lot to unpack there, but basically they're saying that the first 3 terms of the geometric series is 3 more than that of the arithmetic sequence. So what we're going to need to do is take that geometric sequence and add 3 to it. 3 more means we add 3 to it, not 3 times more, but 3 more. And then we are going to make that equal to the first 3 terms of the arithmetic sequence. So for the geometric series, the first 3 terms are 12 times r and 12 r squared. Okay, and they said that that geometric series is 3 more than the arithmetic series. So the arithmetic series is 12 plus d, and 12 plus 2d. Okay, and you can just string them out like that, but remember that that's your second term, that's your third term. And they said that if we added 3 to the arithmetic series, it would give us the same value as the geometric series. So this is the equation that we've got there. Unfortunately, this is just one equation, and there are 2 unknowns. So we need to go look at some other information that can help us to get d in terms of r. Yeah. They tell us in the previous question they tell us in the previous question that both of the first 2 terms of the sequence are the same. So in other words, that geometric sequence, the second term 12r, is equal to the second term from the arithmetic sequence 12 plus d. Okay. And this we can use to get d in terms of r really easily. We can say that d is equal to 12r minus 12. Okay. And we get that just by bringing the 12 over. Now what we can do is, first of all, we'll just simplify this a little bit. 12 plus 12r plus 12r squared. Add up all the numbers on the right there, so we have 24, 27, and 36, 39, okay, plus 3d. And we also know that d is equal to 12r minus 12. Okay. Next thing we're going to do there is we are going to expand and simplify. So if we bring that 39 over, okay, let's expand first. 12r squared, 39 plus 36r minus 36. Okay, and over here, 39 minus 36 is equal to 3. Okay. So on the left hand side, we've got 12r squared. 12r minus 36r is going to be negative 24r. And then 12 minus 3 is going to give you 9. Equals 0. And from here, we can simplify. Always good to put it in standard form. We can divide throughout by 3. We get 4r squared minus 8r plus 3 equals 0. And then we use the quadratic formula there. And we get two values. R is equal to 3 over 2, or R is equal to a half. Alright guys, thanks very much for going through these with me. If this helped, please like and comment, and we will see you in the next one.